Hey, good morning, everyone. Uh, okay, so we are going to continue the higher order differential equation. Okay. Um, yeah, I think last time we finished the this undetermined coefficient, and this is some of the example that you can try. Is my voice clear? Because I now difficult to speak because I just get surgery in my dental, so it's my face a little bit swollen, right? Yeah, the wisdom tooth surgery. So this is the last time, the variation of parameter. So variation of parameter is when you have the differential equation and then the right side is having some functions that is not going to be determined by the previous method, which is the undetermined coefficient. For example, if you have like tangent, secant squared, or other function that cannot be determined with the previous method. But anyway, you can try the variation of parameter in any conditions, especially for second order differential equation. You can try this method. Okay. So let me give you an example how to use this method. So solve using variation of parameter. Okay, so first, as usual, we can start working this differential equation with the constant coefficient or the homogeneous part, which means that we are going to have the auxiliary equation, which is m squared plus 4. And we know that this will be repeated roots. So m1 equal m2 equal to. So our yc, our complementary solution will be c1. And the second one should be multiplied with x. So c2x e to x. And then to work with the variation of parameter, we need to let this two solutions inside the complementary as our y1 and y2. So let y1 equal e with power 2x and y2 is x up. Okay. And then we need to describe this y1 and y2 in Wronskian. So let's write the Wronskian determinant. So this is y1, this is y2. The second row is the first derivative, okay, of the first row. So let me write with different color. So this will be 2, and this will be, maybe let me make it a bit fun. This is going to be 2x e plus e. Okay. And in the Wronskian, we can find the determinant by cross multiply and then subtract. So 2x e for x plus e for x, y it's gone, and then minus 2x e for x. So we can cancel this, and we get the Wronskian result is e with power of 4x. And then we start taking another Wronskian, now using the Cramer's rule. Okay. Using the Cramer's rule for the first one, we let this one is 0, this one is x e to x, this one is x plus 1. We change the first column with this. And then we find the Wronskian. Again, we find the determinant. This will be 0 minus x plus 1 x e for x. Okay. Or this is w, this is w1, so this will be negative. And the same way we are taking the w2. Now the column, we are going to change the second column on the Wronskian. So the first column will be the same as the original one, so e. Now we change the second column with this. So we cross multiply. So this will be x plus 1 e to the power 4x. Okay. And now we can find the u. Okay. We find u. So remember that our goal is to find this. Okay. So our goal is to find our yp, which is composed on u1 y1 plus u2 y2. So this is our goal. Okay. Our goal is this. And from this w, we can find our u. Okay. So u1, let me write here, u1 prime. Okay, u1 prime, if you remember, this is w1 divided by w. So this will be negative x plus 1. W is e with power of 4. So we can cancel. So we can have negative x squared negative x, right? That is u1 prime. u2 prime, or maybe let me solve this. u1 will be, so we can integrate this one. So negative 1 over 3 x cubed, negative 1 over 2 x squared. Okay, that's u1. Now u2 prime is w2 divided by w is x plus 1 then we can cancel, and this will be x plus 1. So u2 is half x squared plus x. Now we can rewrite the yp with this u1 and u2. So let me write here, yp is u1 is 1 over 3 and y1 is e to 2x plus u2 and y2 is x e to x. Okay. This is only yp. So if you want to write the whole solution, don't forget to write y equal yc plus yp. Okay. So it means you need to plus the complementary solution, which is this. Okay. This yc, and still it has some constant that is we can know that if we have the set of value. Okay. If we have the boundary value. So the steps for the variation of parameter is basically the Wronskian, and then solving with the Cramer's rule in matrix. If you remember the Cramer's rule, to solve the W1, we change the first column with 0 and the function on the right side of the non-homogeneous equation. And for the W2, you change the second column. Okay. Now after this, it will be the last method in the higher order. So perhaps we are going to have a quiz later. Maybe not this week, next week, but Thursday. Okay, Thursday. Because now we have the November, so our goal is having I think I think 21 of December, that is not 20, 19, this the Tuesday class. 19 of December, that is actually my goal for this class, if we can make it. So that will be the final exam, 19th of December. So before 19th, I need to have like at least one more quiz. So this second quiz will be the higher order differential equation. And since the quiz only 1 hour, so I think I will just prepare maybe 3 questions. Okay. Based on the experience that we have the first quiz, maybe sometimes maybe the question is not difficult, but maybe too long to write. So I need to prepare maybe just a few questions. Okay, any question from this one? Okay. So this one actually works well with the functions that can be determined easily, the yc. So you can figure the y1 and y2, that is going to be the basis foundation for our Wronskian. And especially for the function that easily to derive and easily to look at. We can get easily what will be in the result here. If you feel like you have a choices, you have a choices, like for example, some x undetermined coefficient, you can work with this. But if you feel that when you do this Wronskian maybe too complicated, then you can just choose the other method. So especially for the second order, as the second order differential equation, you can have many options. But I think for the maybe third order, fourth order, I think the best way is to start with the undetermined coefficient, and then if not, then maybe you check the other one. Because if you have like more than if you have the third order or fourth order, y1, y2, and maybe you have y3. So you have the matrix is not 2 by 2, maybe 3 by 3, and it's more complicated, right? So I don't think that is the best way to solve with it using this. So if you see it's second order, I think this is ideal. Okay, because it's 2 by 2 matrix, not too complicated. If you have like third order, fourth order, you have like maybe 3 by 3 or 4 by 4, and I think that's in matrix not really easy to solve. And I don't think I will give you the third order using variation of parameter 3 by 3 matrix. I personally I also feel it's too much, so I will just like second order using this. It's okay, but for third order maybe use different method. Well, you still can do that 3 by 3 matrix, but I don't think I will give that in the exam. Okay. Okay, now I would like to start with this is another method. Which we call the Cauchy-Euler equations. So let's look at this expression. And what I want to focus is, you see that we start with an and then x with power of n and then d and y dx. And I mean the order and then the power and also the number of the terms, they are the same. The second part also n minus 1, n minus 1, n minus 1. And then until the end, you will see that the first order and then the constant. Okay, and then the right side is a function of x, right? So when you see this, this n equal with this, right? And this n minus 1 equal with this, we can say that this is going to be Cauchy-Euler equation, or Euler equation, or Euler-Cauchy equation. Maybe you reverse that. It's the same. Okay, the same. So of course, as we mentioned, I think previously in the previous sections, we start with the homogeneous form of this Cauchy-Euler, which is let's say in the second order. We have ax squared, and then we have d squared, the second order dy dx plus bx dy dx plus cy equals 0. And then the non-homogeneous one, the same. But we add the function on the right side. Okay. Now, in long story short, I will just get into the idea. To solve this, okay, at least the homogeneous. Maybe this one should be here. Maybe this one should be there. Okay. To solve the second order homogeneous form of this Cauchy-Euler, so first we could think a solution that is perhaps this will work. Okay, x with power of n. Remember, the constant coefficient, we try the solution e with power of x and m. Okay, and we start taking this, and then we take the first derivative, becomes that, and then take the second derivative, and it will be m multiplied with m minus 1 x, and then m minus 2. Okay, now let's substitute this back to the homogeneous one. Okay, so I will write here, so sub to homogeneous form. So we are going to have ax squared, and then this will be m minus 1, and then plus bx. I think maybe let me write here. Plus bx dy dx is m x m minus 1, and then plus c x with power of m equal to 0. Okay, and then if we multiply, and we are going to see that the x squared and xm minus 2, the minus 2 will be cancelled, right? So you will see that eventually this will be a m minus 1, okay, and then this will be x with power of m plus b m, and then x with power of m, and then plus c x with power of m. Okay, if we multiply all together, and now we can factorize x with power of m. So if we look here, then the only way that we can solve this equations is by looking at the bracket here, okay? Because the x with power of m, it's always positive, right? It's always positive. So positive function. So by taking this am m minus 1 plus bm plus c, we could write that this will be the one that makes it 0. Or we can write am squared plus b minus a m plus c equals 0. Oh. So which means that from the equation we are going to solve another quadratic equation. So it's pretty similar to what we have before. The difference is we're having the solution is actually in form of x with power of n, not e. The difference is that. Okay. Previously we have e, okay, with power of some functions, right? Now we have y equal x with power of n. So the expected solutions are, perhaps we are going to see, because it has quadratic equations, actually we have 2m, right? We have m1 and m2. And again, it can be three cases. It can be the distinct roots, repeated roots, or having a complex. So the first case is if it is the roots are distinct and real number, which means this is m1 is not equal m2. So y1 become x with power of m1, y2 is x with power of m2. But of course, in the real computations, we need to add a constant in the front of the equations. Let me give you a quick example on the right side here. And let's just focus on the homogeneous form first. So suppose that we have x squared, y double prime, negative 2x, y prime, minus 4y. So the cauchy-euler, we need to check first. So x squared and then y double prime get the same, 2 double prime, and then x and then y prime, the same order. Okay. So x and y prime, and then we have a constant and then y. So we can rewrite this in terms of cauchy-euler auxiliary equations, and we can write directly. This will be m squared, and then minus. If you see, this is supposed to be plus, right? So plus, let me write plus first, and then maybe let me write a and then b minus a to make it familiar with you, and then plus c. So a is 1, right? And then plus b minus a. So minus 2 minus 1, so minus 3. So I will write this is minus 3m, and the plus c is minus 4, so minus 4. So this is a, b, c. Okay. And now we can factorize, I think, easily. So we get that m1 is, let me write negative 1 first, and the m2 is 4. So our our solution for this homogeneous form are c1 x with power of negative 1 plus c2 x with power of 4. So how to notice when you are using the cauchy-euler? How to notice that? To notice that, you see that we have the x and then y in some order. This is second order, x squared, and x and y prime. So you see that this is definitely a cauchy-euler equation, as we mentioned at the beginning. Okay. Okay. Now the second case is if we have the repeated roots. Okay, the repeated roots. So since it is very similar to what we have in the constant coefficient, the only difference is the result. The result is in x to the power of n. The constant coefficient, the result is e, right? We have in the exponent. Okay, let me give you the second case. This is for the repeated real roots. This is when m1 is equal to m2. Okay, so let me write the am squared plus b minus a m plus c as a is equal to 0. So the m1 2 is basically negative b minus a plus minus this quadratic equations to find the roots. Okay, if the roots are repeated, then this one here, the discriminant is equal to 0, right? So we can write the roots are negative b minus a over 2a okay, and then look at the cauchy-euler expression. So we are going to manipulate this expression and rearrange. We divide, multiply with 1 over ax squared. So we will have y double prime plus b over ax y prime plus c over ax squared y. Now according to the reduction of order, and then we find this one is our p of x, if you remember. So p of x is p over ax, and if we take the integration, this will be b over a ln x. Okay. And by reduction of order, with y1 is x with power of m1. Okay. Then y2 will be x m1 integration. This is x and let's try to solve this, simplify. The p of x is b over a, so minus b over a ln x. And then this will be multiplied with x, negative 2m1 dx. I will move this b over a going there, so ln and e will be cancelled. So this will be x negative b over a and x negative 2m1 dx. Now this 2m1 or m1, we can get from here that 2m1 is negative b minus a over a. So we can substitute with this. Okay. Substitute this. Okay. So we substitute back here. So negative will be cancelled. So b minus a over a dx. So we can compute the power. So negative b over a plus b minus a over a. So this will be b is cancelled. So we have negative a over a or negative 1 or x with power of negative 1. So we get, finally, we get that this will be 1 over x dx. Or we can write the y2 is this. Which means whenever you get repeated roots, you can write the first one and then just multiply with the other. Okay. This for y2. So you will have the whole solution y1 plus y2. So y2 you need to write like that. So the general solutions. So solution, or let me write. So solution c1x m1 plus c2 x m1 ln x. So this is solution for repeated roots, okay? Repeated roots. Let me arrange this to make it more space. Let me write there. Let me write here. Just a quick example, okay, how to use these repeated roots. Let me just write the equation first. Okay, that's the example. So as we know, first we need to check the cauchy-euler form. It has squared. This is second order. This is the first linear, and this is the first derivative, and this is the delta constant and y. So we can write this a, b, and c. We can write the cauchy-euler. So a is 4. B is 8 and C is 1. So this will be the form for the auxiliary equation. So this will be B minus A and then plus C equals 0. This is 4m squared plus B minus A is 4. And I think this is factorizable, so we can have this. Okay. So of course, this is repeated roots. We have this, the m1 equal m2. So m1 is negative 1 over 2, which means that y1 is x with power of negative 1 over 2. Now, because this is repeated roots, we can directly write the general solution. So solution is y equal c1x negative 1 over 2 plus c2. Write the same thing and added the ln x, just like that. Okay. So basically, in practical computations, you don't really need to write the rejection of order. Okay. You can just write the conclusion, which is this. The repeated roots just multiply with the ln. Okay. So this is the second case, repeated roots in the Cauchy-Euler equation. So again, now we are still discussing the Cauchy-Euler equation, which is very similar to the constant coefficient. The difference is our proposed solution is not e with power of like mx or m1x, but we have the x with power of m1. That's our solution. And if you have repeated roots, basically we are going to write similarly, but we multiply with ln x. Okay. Now the complicated one is the third case, in which we have the complex. Okay. The complex. Okay, now the third one. So let me write third one. So the third is we have the conjugate complex roots. So if roots of auxiliary equation is in the form of alpha plus I beta and m2 is alpha minus I beta, where alpha and beta, they are both positive and real numbers, then our proposed solutions are c1 x with power of alpha plus I beta plus C2 x alpha minus I beta. But the problem within this solution are we having the I, which is the imaginary number, right? We want to make the solution in the whole solution in terms of real numbers. So we are going to use the Euler formula as we did before. So we can rewrite, first we can write identity that in x with power of I b, we can write in terms of e. So we take e and then ln x and then I b. So we can write e I b ln x. So by doing that, we can get the x IB is equal to cosine beta ln x I think we can take a break. So this is actually the same as we mentioned in constant coefficient. The difference is we add the element. So in the previous one, we have the e with I beta x, and then we have this cosine and I sine, and cosine negative I sine for both cases. But now we have the x with power of I beta, which is we can rewrite as is e, which means we are going to substitute this inside here. This be beta ln x, and then we have this too. And with the same approach, we can get, if we add and subtract, okay, we can get, so let me write here. If we plus, we get 2 cosine beta ln x. And if we subtract, okay, so we can write these solutions are x alpha plus C2x alpha minus beta. Okay. For C1 equals C2 equal 1 and C1 equal 1 and C2 equal negative 1, we see that the y1 will be x alpha x I beta plus x negative I beta, or 2x alpha cosine beta ln x. And y2 is x alpha and this is x I beta minus x negative I beta, or we can rewrite in 2 I x with power of alpha sine beta ln x. And then since this should be linear independent or in the Wronskian between the x alpha cosine beta ln x, and x alpha sine beta ln x. If we take the Wronskian, both of this, we get that this will be not equal to 0, which is linear independent. And since beta is also positive in interval 0 to infinity, then y1 is so general solution. Okay, that's the general solution. So again, you only need to find the relations alpha and beta from the differential equation. And how to get the alpha and beta? We need to find the roots first. The roots from the auxiliary equations. So the goal is actually why we need to write in terms of this cosine sine. The goal is actually to remove the imaginary number using the Euler formula. And then from this argument, because this one is linearly independent with this one, since this is, if we take the Wronskian, it's not equal to 0, and the beta is positive in 0 to infinity, then we can argue that it's y1 and y2, okay, this is the solution, and we can write the general solution as this one. And sometimes the auxiliary forms, the am squared plus b minus am plus the constant, sometimes it doesn't work. So I think it's best to start from the scratch, which means you start from substitute the y prime, y double prime, one by one. Let me show you what I mean. Okay, what does it mean? So for example, solve 4x squared y double prime plus 17y equals 0, and we have the initial value. Okay, now if you look at the form, we have double prime, we have x squared, we have a constant, we have y, but we don't have the first derivative. We don't have y prime. So I think it's best to start from the scratch. What does it mean? It means that we are given our proposal, which is y equal to x with power of m, and then we're going to substitute manually. Okay, so we substitute, sub back to here. Okay. So 4x squared so 4m minus 1 x with power of m and then we get the auxiliary now, right? This is the auxiliary. So we can start the auxiliary, finding the roots. I think we are going to complete the square, just plus 1, plus 1. This will be similar to what we have before, right? So 2m minus 1 right, squared, negative 16. So 2m minus 1 is, so 2m, it will be 1 plus minus 4i. Or m1 will be half plus 2i. m2 is half minus 2i. And from the previous, the complex conjugate, you can identify that the alpha is half and beta is 2. So we can write y x with power of alpha, it's half. This is C1 cosine 2 ln x plus C2 sine 2 ln x. And then take the initial value. And then this is negative half. So checking the x equal 1. Cosine 0 is 1, and sine 0 is, so this will be -1. So C1 is -1. And C2 is, we use different color. So -12 equal so if we take the first derivative, so let me write on the right side, maybe right here. So y prime is, it's a little bit crazy here. So 1 to square root of x multiply and then we have a product rule. Okay, I think I don't have space here. I think I will move back to here, and plus square root of x, and then differentiate the inside, negative sign, multiply with chain rule, plus C2 cosine, and multiply with chain rule again. I think I should have simplified first, but anyway, we can just try. X is equal 1. This is half. This will be 0. So C1 is -1, so -1, plus C2 is 0, and plus 1. This will be 0, right? 0 plus C2 multiplied by 2. Okay. It should be equal to -1/2. So -12. So C2 is -12 plus half, it's 0. So C2 is 0. So from C1 and C2, so solution is C1 is -1. We write x with power of 1/2. So C2 is 0, so which means there's only cosine. So cosine 2 ln x. Okay. Okay. I hope you get it. Did you get it, this one? I just differentiate and take the product rule. It's quite long. Okay, now we solve all the homogeneous part in the Cauchy-Euler. Now the next problem will be if we have the non-homogeneous one. So if we have homogeneous form and we can solve with the Cauchy-Euler equation, then we can identify whether the roots will be distinct or repeated roots, or like this one we have the complex roots, right? So we solve the homogeneous part. For the non-homogeneous one, we are going to use the homogeneous solution, and then we're using the variation of parameter that we did in the previously. So we are going to use another method to solve. So I think I will just give you the example by solving the problems. Okay. But maybe if you want to write this first, you can write. And we can have several examples, and actually we can move to the last part of our course, which is the Laplace transformation. But maybe we give you some. I will give you some example first. Can you check if their first derivative has some problem or not? Is it correct? This one? I differentiate from that y prime. I'm using the product rule. So differentiate this, write the rest, and then write the square root of x, and then differentiate the inside. I think it should be okay, right? Then take x equal 1, put here, put there. All these sign will be 0, right? Okay. I think correct. Yeah. I think the textbook. Which one is better, this one or this one? I think this one. I go here. I'm correct. Textbook is wrong. The question is actually this one. The question is this one. So sometimes why the textbook has many editions? Because sometimes they made some mistake. Okay. So that's why you need to read carefully and then solve it. Yeah.
What happened to the C1? Why is it not minus? The general solution.
So minus.
The general solution.
Ah, it should be minus. Right. So this should be minus. Okay. Can add. I forgot to write the minus. Okay. Okay, let's take another example. Okay. So, example, solve So if you check this equation, so the first thing is we check that this is Cauchy-Euler on the left side, right? This is Cauchy-Euler. So we can write first, this is Cauchy-Euler. Which means we can solve the homogeneous form of this. Okay. So we can solve the homogeneous. We can write this. This is A, B, and C, right? So A is 1, B is -3, and C is 3. So we can write the auxiliary is, let me write first too, so that you can familiarize. So AM squared plus B minus AM, and then plus C. So because we have a complete set of the Cauchy-Euler. But whenever you find maybe some time in the middle and then you don't write the notes, you forget this part, you can get this form by taking the solution as the y equal x to the power of n. Differentiate, and substitute to this one. Okay. Will be the same conclusion. So we take A is 1, so we write m squared. B is -3, A is 1, so -3 minus 1, so -4. So plus 3. Right? -3, -4, yeah. So M1 is 1, M2 is 3. Okay. So it's just a normal. So YC we can write C1x plus C2x with power of 3. And then to solve this, the whole non-homogeneous form, we can let this equal y1, this is y2. So let y1 is x, and y2 is x cubed. Now let me write the whole equation again. So equation is x squared y double prime plus minus 3x y prime plus 3y I will divide all the form with the x squared. Okay, I will remove the x squared, so I will multiply with 1 over x squared. So this will be y double prime plus 3y. This will be 2x squared e to the x. And now we are using the variation of parameter. Okay. So taking this as our function, so using the variation of parameter, y1 is x and y2 is x cubed. So first we can write the Wronskian. As usual, we can write the Wronskian. The first Wronskian will be taken by x and x cubed. Differentiate, become 3x squared like that. And then find the determinant. This will be 3x cubed minus x cubed, 2x cubed. And then W1, we change the first column with the 0 and the f of x, which is 2x squared e with power of x, and then x cubed, 3x squared. So 0 minus 2x5 e to the x. Or we can just write negative 2x5 e to the x. And then W2 is x, 1, and 0, 2x squared e to the x. this will be 2x cubed e to the x. And then from here we get the u1 prime, which is w1 divided by w. This will be what? Cancel. Negative x squared e to the x. And u2 prime this is e to the x. I think the u2 prime easily you can find the u2 is e to the x. We can just integrate, but for this one we need to integrate this, right? So u1 is integrate of this, or we can, if you feel confused about the negative, let me write like that. And how to integrate this? I hope you're still familiar with the calculus 1. Okay, so idea is we can take this so u1 is negative x squared e to the x negative 2x e to the x plus 2e to the x. Or let me write there. Or this will be negative x squared e to the x plus 2x e x negative 2e x. Okay. So our yp is u1 y1 plus u2 y2. So we need to combine. Y1 is x, y2 is x cubed, right? So yp is x, and then plus u2 is just e to the x. So x cubed e to the x. I think we can simplify it first. This will be negative x cubed we can cancel this. So yp is 2x squared e to the x negative 2x e to the x. We can combine total solution. Y is c1x plus c2x cubed plus 2x squared e to the x minus 2x e x. think because in the exam, anything can happen, right? I mean, how to solve the problem. So maybe for some parts, I will guide you to which method that you need to do first, and then this, and then maybe the other one you can choose with, any method. So I think this that will be helpful if you are still doesn't have any clue how to solve the differential equation. Okay, any questions from this one, this part? Okay. Now, another typical questions is the question will be reversed. So they have the solution, and then you need to find the differential equations. For example, so if y is c1 plus c2 x with power of 5, find homogeneous cauchy-euler differential equation. Okay, now we have this solution. Y equals c1 plus c2 x to the power of 5. Now we need to guess. We have at least we are going to have two roots, right? We have two roots. We have m1 and m2. Right? We have m1 and m2. Remember that all the original equations start with y equal x with power of m. Okay. So imagine that this part x with power of m is substituted here. So we get that the second root will be 5, the m, and the first one, I think this should be 0, so that it has a constant 1, right? So from that expression, we can get that this m1 is 0 and m2 is 5, which means we can write from the m and then m minus 5 that this is the equation, right? To find the m equals 0 and then m equals 5. So we find that this will be m squared minus 5m equals 0. And remember that this is a, right? This is a. This is b minus a. Okay? So we can write that a is 1 and b minus a is negative 5. And c is 0. So no c, right? So since a is 1, so b is negative 4. So we get a, b, and c. So we can write all those a, b, c in the normal Cauchy-Euler. So a is 1, so x squared y double prime. B is negative 4, so negative 4x y prime. And c is 0, so it's just equal to 0. So this is the differential equation for the homogeneous Cauchy-Euler. Okay, last one, but just example to see how you can solve. Okay. Solve let me give you a couple minutes and then we are done. Okay. So all the higher order differential equation, the method, we finish. As I mentioned, next week Thursday, maybe a quiz. So the topic will be the higher order differential equation. So the topic for Thursday this week will so Thursday will be we move to Laplace, okay, Laplace transformation. Laplace, and next Tuesday we are going to continue Laplace and maybe some review on some method we have, and maybe this week I give you some maybe representative question for practice. Okay, for practice. And I don't think Laplace will be finished the whole section. Maybe 75% maybe. And we are going to see whether we need to have like another makeup class later, maybe. Anyone try this one? Just to make sure that we are okay with this question. This is a standard question, the cauchy-euler. Okay, you should be able to do this. Okay. Okay. So this actually so we can write from here. So a is 1, so m squared. B minus a, so -3, -1, so -4. C is 4. So we have this, right? We have repeated roots. So m1 equal m2 equal to 2. So our proposed solutions is c1x squared plus c2x squared and then ln x, okay, because repeated roots. And then check when x equal 1, this is 0, this is equal to 5. So c1 is 5. And then check the first derivative y prime, 2c1x plus c2 2x ln x plus x, right? And then check also when x equal 1. So 2c1, c1 is 5, so 10 plus c2, this is 0, this is 1, so this is 1, this is equal to 3. So c2 is -10 plus 3 is -7. So y is 5x squared minus 7x squared ln x. Okay, that's it. If the question like this, it should be easy, right? Or no? More or less, is it easy? Right? Okay, if there's no, is there any question? Yeah, all the higher order. But I mean, not all, but from the whole thing, only 3 questions. So I don't think I can fit all the things inside. And you can prepare the A4. Okay, the same thing, A4. And then each method, I think you need to write. If you forget one, maybe there's one question about that. So I think just write all the methods. Okay, all the methods. And then please prepare the notes very well. I think last year some students they prepare maybe in a rush, so they don't even can read their own writings. So prepare very well. Okay, prepare the notes. Okay.